All right, this is Connor with another video for ASEN 3111, preparing for exam 1. All right, so I'm going to be talking in this video about just some fundamental aerodynamics concepts, right? So I'll be talking about aerodynamics in general, what we care about in aerodynamics, parameters of flow, what flow really means to us, and as also be able to move through conservation of mass and momentum, the integral forms of those, all the terms, and then I'll also touch on Bernoulli's equation and some of the assumptions that must hold for Bernoulli's equation to hold, right? So with that, I think I'll just get into it, right? So aerodynamics, and I have the definition written right out in front of me. This is the study of the properties of moving air. Study of the properties of moving air, specifically moving air over solid bodies. All right, we care about how air is interacting with stuff we put in it, right? Planes, missiles, bullets, anything that's moving through the air where the air is having an effect on it. I went totally in like the war zone direction with that. Parachutes, gliders, lots of other more benevolent ideas, right? But we care about how the flow is interacting with them, right? And with that, we have these four kind of fundamental, I don't know what the word I'm looking for is, fundamental characteristics of a flow that we care about. So there's the pressure, there's the density, the temperature, and the velocity. Right? All of these things define the flow. Right? So pressure is the force per unit area due to, this is from particles impacting a surface, right? So force per area from, and actually I'll be more complete with that, from time rate of change, ROC, of momentum, MOM, or particles impacting a surface. Actually, I'm going to say and, because it is the combination of both of them. And particles right? Density is the mass per unit volume of a flow. Temperature is the change in kinetic energy due to random particle movement, right? So this is kind of like the average, so change in KE due to random particle motion, right? So this is kind of like the average jostling of particles as they sit in the flow. They're bouncing around, and the faster and more energetically they bounce, the higher their temperature is, right? This is not to be confused with heat, even though I'm sure you're confusing it with temperature over in your thermodynamics class. Heat is like the total energy, whereas temperature is just kind of like that instantaneous change in kinetic energy. It's like the instantaneous, what are the particles doing right now, right? And then velocity, how fast and in what direction. Is the flow moving? And we usually talk about this flow in like an organized fashion, right? We're not so much concerned with turbulent flow that's going all over the place because it's separated off the back and it's making eddies and stuff like that. We don't talk about that so much in this class. We'll get into it. We'll get into it just slightly, but these are kind of the 4 big things, right? Good to have definitions for these written out. Maybe take them from a book. Maybe don't take them from me because these are kind of ad-libbed. But yeah, this is what we care about in aerodynamics, right? So moving along, move on to conservation of mass and momentum. Specifically, I'm going to focus on their integral forms. Well, let's write that out. So we're going to have integral over the closed surface of rho v ds, where ds is that's a capital S, so it's a differential area. This is equal to the partial respective time of the volume integral. Volume integral of rho dv, right? Conservation of mass. Right? So what is this talking about? So what this is essentially saying, let's look at the left-hand side first, right? So we have density. This is kilograms per meter cubed. We have velocity, meters per second, and we have area, meters squared, SI units, right? So if we multiply all these together, this is going to cancel with these, and we're going to end up with kilograms per second, right? This is one way of interpreting it. You can look at the units and how they cancel out. And what this tells us is this is a mass flow rate, right? And we can kind of figure this out. If we have some closed surface, right? So we've got our bean, and our bean's it's got some depth, right? And a little shine there. And then we'll draw a little differential surface. We're basically asking, we're asking what is the mass flowing out of this surface, right? We have some density inside this function, and it's moving at this rate v, and it's moving. We care about the amount of that is moving out of the surface, right? So how much is leaving this surface? Right, and since it's a closed surface, we can also talk about it in terms of a volume, right? In the same sense, so we say, what is the time rate of change of a similar quantity? This is rho times, so actually let's use units. This is kilogram meters cubed times kilograms, right? And so we end up with, oh my gosh, meters cubed. So we end up with kilograms, right? With differentiating with respect to time, we get kilograms per second, right? So this is telling us we have this volume integral, right? This is how much mass is inside this volume V. And you can go back to we have a line, surface, and integral video, or a volume integral video that talks about this a little more in depth, but how much mass is in here and how quickly is it changing, right? You can imagine if you have mass leaving a surface, the amount of mass leaving, the rate at which mass is leaving is going to be exactly the rate at which mass decreases inside that surface. That is the conservation of mass. And I'll clean this up so you can look at it more easily. But that's what we're talking about here. How much mass is leaving, and that is going to be equivalent to the time rate of change of mass inside the volume, right? So we can talk about this in terms of, we can assign some words here. So this is time rate of change of mass in volume V. And then this is the rate of mass exiting the same volume V enclosed by S, right? So if we just have mass moving out of this thing, the amount that goes out is the amount that decreases inside. Those transition at the same rate, right? Moving on, let's talk about conservation of momentum, right? So this one's a little bigger. This is actually going to take a little longer for me to write out, so I think I'm going to cut and then return with all the terms listed out because I'm a time saver and I'm efficient, and anyone who says otherwise is lying. So let's talk about each of the terms here. This is the conservation of momentum. Cons of mom. All right, so we have a few different terms here, right? And actually, we'll save this till the end. This is a little special thing that I like to remember, put on my crib sheet. But essentially, let's look at this term, right? So we have the time rate of change of the, so we have density and velocity right here. We know, or density and volume right here. So these two together make mass, and then mass times velocity is momentum. So mass times meters per second, and then this is the time rate of change of momentum, right? So this is the change in momentum due to basically how the flow is changing. So we have momentum here, and this is the time rate of change of momentum, all inside this volume, right? And we call this term the time rate of change due to unsteadiness in the flow, right? Moving along, we have this next term right here. So we have mass times velocity moving through a surface, right? We remember from up here, mass, velocity, surface, this is a mass flow rate, right? Kilograms per second, right? And then we also have this nice, and I'm forgetting the dot product there, we have a nice little velocity out here. So this is like a, what am I doing? So this, we have we're basically looking at like, this is like the, and I am forgetting a few units here. This is like our momentum, all moving through this surface, right? And the rate at which it moves through the surface is quantified by the velocity that it moves through that surface. Right? So we call this one the net flow of momentum out of volume. What is the word I used up here? Enclosed by S. All right. Moving along, we have another term. So this is pressure, not density, right? And pressure exerted over this surface. These are the pressure distribution forces. And recall that a force, so we can look back at Newton, who said dp dt is equal to F, and here P is momentum. I think actually, yeah, this will be fine. Just note, that's not pressure, that's momentum. Right, so if we have forces, we have a pressure over this area. This is a force. This equates to momentum. So this is pressure dist forces. Right? I'll move this out of the way. Talk about these last two terms. So then this guy, this is body force per unit mass, right? Per mass. Multiplied by the density, that's how we kind of get like the mass per volume. So we have force per mass times mass per volume. So we have force per volume times volume. This is all the body forces acting on everything inside this volume. So we'll call this one just body forces, which also impart a change in momentum, right? And then finally we have our viscous forces, which is pretty self-explanatory because it says viscous, but this is like the, everything having to do with viscous losses, right? There's some friction force happening that we don't model very well, and people like Dr. Evans work really hard to model it, and they're so good at it, but they do not make that information privy to undergrads, right? So don't worry about it. But this, you should know, this is due to friction, right? Which we just don't model very well with airflows, right? So we have all these together, and what I like to call these, I like to say unsteady, because this is usually the type of thing you would see on the conceptual side, right? No crib sheet, right? Flow out minus pressure and body, right? And I don't really have a little thing for over here, but this is where this guy comes in. Let's bring it back around. Right? UFPB UFPB, right? So easy to remember. It's just UFPB, right? Stuff like this, just pick one word out of these that you can relate, and also try to make sure that you understand the units. I think that's really helpful if you can pick out the units going into it, and they say, tell us what each term means. You can say, okay, this is the mass, moving. I see that it's like mass times velocity, right? So this is it's the time rate of change of that. So it's like the rate of mass moving and the rate at which mass is moving is changing, right? A lot of things going into there, but unsteadiness is a good one-word thing where you can kind of remember, oh, this is what's happening, right? Same with this one, net flow out. We have mass moving at some velocity, and over this, through this surface S, and as it flows out, we get this momentum is leaving the surface, right? And that's counteracted by the pressure acting on the volume, the body forces acting on the volume, and any viscous effects, right? So finally, Bernoulli's equation, right? So Bernoulli's, very nice. You guys learned this in 2004, last year, right? Basically goes, we have P1, this is static pressure, plus 1/2 rho infinity. This is free stream density times V1 squared is equal to P2 V2 squared, right? Where actually point 2 can be anywhere along a streamline, right? So if I have my point 1 over here, my point 2 over here, this I can always relate point 1 and point 2 if I have these characteristics of the flow, right? I could go from one point to the next, right? So what assumptions go into this, right? We have a few things. One is that we're assuming this density doesn't change between these 2 points, right? So that means assumption 1, incompressible, right? Number 2, basically what this says is the total pressure stays the same throughout this whole thing. So we have this is essentially our static and dynamic pressure. And in order for that to be true, we can't have any losses, right? So that's another one we have to say inviscid, no friction. 3, another thing that kind of, we can't let this streamline can't be changing with time, We can't have anything like T1, T2, T3, right? We need it to be completely steady for all time. And for that, we say steady. I already gave it away. Steady, right? And the last one that also comes back to kind of keeping our total pressure all the same is we can have no body forces. Right? This is another great one they love to ask on those exams, on those closed book parts. But as far as the fundamentals go, I think that's a pretty good cap. I think that captures, what some of the bigger picture stuff that you might have to know right off the top of your head without a crib sheet, right? Thanks for watching. It's always a pleasure to make these videos. If there's anything you have questions on, definitely reach out to us. You have our email in the I think description of the video as well as in like the bio of the channel. Come to office hours. Our office hours are listed on the Engineering Fellows website. You can Google us. It's under the aerospace calendar. Talk to us about anything. We love to hear what you're going through. We went through it, and we want to make sure you guys don't struggle as much as we did. That's always we're always trying to pass it forward. Or is that what? Pay it forward. Pay it forward, right? All right, so it is 2 a.m. on Tuesday morning. It's time for me to go to bed. Thanks for watching. Good night.